Hello, everybody. So we're going to talk in this video about using trig identities. We'll hear phrases like verifying identities. Eventually, we're going to use these identities to solve equations, which we should talk about what that means exactly. And our main goal right now is just to get used to manipulating expressions with trig functions in them using some of the relationships, the identities that we've already identified. And we'll talk about those in a minute. But I just want to make clear what an identity is. Okay, right? So mathematically, when we talk about an identity, it's going to be an equation relating two expressions that's always true. So maybe I could say it with two expressions that are always true. And I should say on the domain, right? So sometimes you'll have things like, well, let's just do a couple examples and I'll talk about on the domain in just a moment. If we have x plus x is equal to 2x, this is an identity. It's always the case that if you add a number to itself, it's the same as multiplying that number by 2, right? It doesn't matter what the number is. If you double it or you add it to itself, you're doing the same thing, or you end up with the same results, right? Versus, let's look at similar kind of equation. This is not an identity. This is not always true. All right, it's true for some values of x, but it's not always true that multiplying x by 2, multiplying a number by 2 is the same as squaring that number, right? For instance, the number 10, 2 times 10 is 20, 10 squared is 100. On the other hand, this is true for the number 0. Right, so let's write this one's always true. This is just true for 0 and 2. Right? So that's not an identity. Identity is always going to be true. Notice we can solve both of these, and let's just see what happens. 2x equals x squared. I might subtract 2x from both sides, factor out x, and we see then we get the result of x equals 0 or x equals 2. What happens if we solve an identity? All right, so if I'm solving this for x, so maybe I think, oh, let's get all the x's on the same side. So I subtract one of the x's, I'll have 2x minus x is just going to be x. Let's get this other x over there. I end up with 0 equals 0, right? And this is what happens when you solve an identity. You find something that's just always true because you started with something that's always true. You have the same things. So ultimately, if you have two of the same things on either side of an equal sign, you subtract them both, you get zeros on both sides. Or depending on how it looks, you might get 2 equals 2 or something else like that. That's always true. So anyways, this is what we mean by an identity. Something that's always true on its domain. We'll just do a quick example. If I write something like 1 over x plus 1 over x is equal to 2 over x, this is basically the same thing as what I have here, more or less. But notice now the number x can't be 0, but it's true on both sides. And so on the domain of these expressions, this is always true. So that's the only, we have to be a little careful. And this shows up in trig when we have things like tangent that's not defined everywhere. So we'll have an identity defined involving tangent. It's true wherever it's defined. So let's look at some of the identities we've seen already. We've already collected quite a few, and we're going to in the next few videos, not in this video, I don't think I'm introducing any new identities, but we will be gathering quite a few. So I won't write these ones all out, but we have, well, let's write them out. Our trig definitions. For instance, tangent of theta is equal to sine of theta over cosine of theta. We can think of this as an identity when it's useful in an equation or expression. Secant of theta is 1 over cosine of theta. Cosecant of theta is 1 over sine of theta. And cotangent of theta is equal to 1 over tangent or cosine over sine, right? All of these are identities. And what we use identities for is we can replace one with the other, right? When for instance, thinking back to this one, if I have some equation I'm trying to solve, like x plus x equals 9, because this is an identity, x plus x is equal to 2x, it means they're always the same thing. So I can replace x plus x with 2x and then divide by 2 to solve this, right? So this is, I'm trying to lead us where we're going to go. We're not doing that quite yet, but we're going to solve equations. It's one of the uses of being able to manipulate with identities. And so when it's useful, you can replace one thing with another thing that's equal to it. That's the same thing. That's identities. Okay. We've also seen the Pythagorean identities. So we've got sine squared theta plus cosine squared theta is equal to 1. We also have tangent squared theta plus 1 equals secant squared theta, or 1 plus cotangent squared theta equals cosecant squared theta. Okay, so we have these three identities, and we can take these as truth. We've gone through them a bit in the past, and so we can, anytime we see sine squared plus cosine squared of an angle, we can replace that with 1, right? And all of these, okay? And then we also talked about our even and odd relationships, and we can think about these as identities, right? So for instance, we've said, so all of our odd functions, we have sine of negative theta equals negative sine of theta. We have cosecant of negative theta equals negative cosecant of theta. Tangent of negative theta is equal to negative tangent of theta. And cotangent of negative theta is equal to negative cotangent theta. And then the even ones, we have cosine of negative theta is the same as cosine of theta. And secant of negative theta is equal to secant of theta. Right, so in all of these cases, these are identities we already have, we're free to use. If we see an expression on one side of any of these equal signs, we can replace it freely with the expression on the other side, right? And in these trig definitions, we see that example of where they're defined, right? For instance, cosecant theta equals 1 over sine theta. This is always true on the domain of both of these. We can call them functions on either side, because neither of them is defined when sine is equal to 0. So we don't really have any problems with that. Just got to keep that in mind. Okay. So what we're gonna do in the next, I'm gonna do 2 or 3 examples in this video, and probably another couple in the next video. We're just gonna work on verifying identities, which is really just practice at manipulating these expressions. So it's a good exercise, right? I think of these kinds of exercises a little bit like, I don't know, if you play a sport, right? If you play soccer and you might practice dribbling around a row of cones, right? It's something that never happens in a game, but we all recognize it's a useful skill to practice. This is kind of that. We're just using this kind of assignment of verifying identities as a way to practice manipulating trigonometric expressions using identities. And I know this is all pretty abstract now until we get into the examples. And let me just give one more thing before we do our first example, a kind of a rule of thumb for how to approach these. We can, when I say rule of thumb, this is something that's not a hard and fast rule. You can definitely find exceptions to it, but it's a good place to start your thinking when approaching these problems. So in a verification problem, when I ask you to verify an identity, what we'll have is some expression equal to some other expression. And I want to show that they're the same thing, right? So the way we'll usually approach these, we will typically take the top complicated side. Let's say, start with the complicated expression, right? So if I look at my expression equal to some other expression, one of them is usually more complicated, and it's usually easier to start with that one. We'll perform any algebra that's available to us, right? So combining like terms, factoring things out, expanding. If you've got some distribution to do, things like that. Maybe combining fractions, but basic algebraic moves. Substitute known identities, right? So replacing something with one of the things from that list I have up above. So you're taking something we already know to be true. In this list that I have up here, we can accept that all of these are true and use them without having to justify it. And we use these to try to manipulate this complicated expression to look like the other expression, the simpler one. If none of these substitutions work, none of these known identities, we can always try converting everything, all trig functions, to sines or cosines, right? Because all of the other trig functions are always, can be written as a combination of sines and cosines, and it might explode this thing and make it look very complicated, but then usually things will cancel out. Excuse me. All right, so let's do one so you'll see what I mean by these. I know it's pretty vague right now without an example in our hands. So let's say I am tasked with verifying the following identity. Cotangent of theta times secant of theta is equal to cosecant of theta. Okay, so this is one we haven't seen before. It's not obviously true. So let's just follow these rules of thumb. So by a slight margin, the left side is more complicated than the right. It's got two factors instead of just one. There's not a lot of algebra to do, right? There's nothing to combine here. There's nothing else to do with these two things. So I might try substituting known identities. And the only things I can really substitute here is the definitions. Cotangent of theta is equal to cosine of theta over sine of theta. Oops. Maybe I'll just write that off to the side. I'm using cotangent of theta equals cosine of theta over sine of theta. And we're also going to use that secant of theta is 1 over cosine of theta, right? So these are substituting these identities, or it's similar to number 4 in this case. They're kind of the same thing. We're rewriting everything in terms of sines and cosines. Okay, so now I've rewritten these. Now I can actually go back in my list and say, well, what else can I do? And I've got algebra to do. There's fractions here. And if I multiply these fractions across, I get cosine of theta over sine of theta times cosine of theta. And then using the rules of fractions, I get this. So maybe I'll just write that. Fractions. Okay, we get 1 over sine of theta. And then by definition, or by the identity, 1 over sine of theta is cosecant of theta. Okay, and so again, this is just our definition. 1 over sine of theta is equal to cosecant theta. And so notice everything we've written is equal to what we started with, right? That's how we organize this. I'm leaving this side blank, just indicating that nothing changes over here. And we end up at the identity that we wanted to prove. Okay, so again, what we're doing is we're starting with an identity we haven't seen before. At each step, we're allowed to use any of the identities that we have already. All right, so that list up above, and like I said, we're about to collect a phenomenal amount more. And we're allowed to use any of the rules of algebra to manipulate things, right? So we have to use those rules properly. But using those, we arrive at the other side of our identity. And so this is what we mean. This is what we mean by verifying it. Okay, let's try another one. Let's show that secant squared theta minus 1 over secant squared theta is equal to sine squared theta. Okay. So this one, I'm gonna do this one in several different ways, because this is also something that's common, is there might be different ways to approach a particular problem. So let's do solution 1. Okay. So one thing I might try first, I'm going to start with the left-hand side. That's our more complicated side in this case. And maybe I'll just use the fact, I'll just use how fractions work. I can rewrite this as 2 different fractions. This 1 over secant squared theta. Well, secant squared theta over secant squared theta is 1 minus 1 over secant squared theta. Well, secant squared is 1 over cosine squared theta. So there I'm using an identity, right, or a definition of secant. This means that 1 over cosine squared theta is just cosine squared theta. And then I also know that we have the identity that sine squared plus cosine squared theta is equal to 1. So I can replace that 1 . Right, this 1 became a sine squared theta plus cosine squared theta, and we get that then cosine squared theta minus cosine squared theta is 0. So we have sine squared theta. And so there we have one possible way to show that these two things are equivalent, right? So again, I used basic rules of algebra combined with a couple of identities. And notice that rule of thumb, I listed them in order. We're really going back and forth around them, right? We might take some poking around to see what happens. But we've shown that these are equivalent. And so anywhere that both expressions are defined, this is going to be true, okay? Okay, that's all I'm going to say about that. Let's take a look at another way to do this one. Let's do it a little differently. And this is only to show you that there's no necessarily correct way to do it. There are typically going to be multiple ways to do it. There are definitely incorrect ways to do it. Our logic has to be sound. We have to be using known identities or algebra along the way. So for instance, here's another method. I'm going to again start with that secant squared theta minus 1 over secant squared theta. And I'm going to replace secant squared theta. I'm going to write this one out because we might not remember this as 1, but we as easily. We have an identity that tells us that tangent squared theta plus 1 is equal to secant squared theta. Okay, so I can replace, I'm going to replace the secant squared in the numerator with tangent squared theta plus 1. That went in for the secant squared, and then I still have a minus 1. All of that is over secant squared theta. Well, now I've got plus 1 minus 1 in the numerator, so I have tangent squared theta over secant squared theta. And let me just rewrite this fraction as tangent squared theta times 1 over secant squared theta. Okay. Well, we just saw what happened to 1 over secant squared theta. Remember this move over here, secant squared is 1 over cosine squared. 1 over cosine squared gets us back to cosine squared. And tangent squared, we know, is sine squared theta over cosine squared theta. And we just said this one is equal to cosine squared theta. And so those cosine squared thetas cancel. We end up with sine squared theta equal to secant squared theta minus 1 over secant squared theta. Okay. And this does not exhaust all the ways there are to prove, to show that this identity is true. But I just wanted to show us that there's not necessarily a best route to get there. I don't know which one of these you prefer. Either one is acceptable. And I know I have at least one more, but I think I'll leave it up to you to find other routes if you're interested. Okay, let's do one more on this video and then call that it for this one. Let's verify that 1 plus sine theta times 1 plus sine of negative theta is equal to cosine squared theta. Okay. So I'm going to start with the left-hand side. It's more complicated. So, and again, I'm about to do this and it might look like I just know exactly what to do, but it's because I tried it before, right? So you might not see exactly what to do the first time. One thing that jumps out at me is that sine of negative theta, and we have those even and odd identities. And remember that sine of negative theta is equal to negative sine of theta. So I'm going to try this. I'm going to replace the sine of negative theta with negative sine of theta. Okay. Well, now notice what I have. I have something like a plus b, a minus b, right? One, in this case, a is 1 and b is sine of theta. And we recognize this as a difference. It's the difference of squares, a plus b, a minus b. You can just FOIL that, expand these terms if you want to prove it to yourself. But what we end up with is 1 minus sine squared theta. Again, that 1 I can replace with sine squared theta plus cosine squared theta minus sine squared theta, right? Using that 1 is equal to sine squared theta plus cosine squared theta. And then of course, the sine squared thetas cancel and we're left with cosine squared theta. And so this 1 plus sine of theta times 1 plus sine of negative theta, I wrote it too far away, but you get the idea, is equal to cosine squared theta. Okay, so just to summarize, the goal with these kinds of problems, what we're doing in this video in the next couple is we're learning to manipulate expressions involving trig functions using the identities we have. And the big idea is you can replace any expression you see with one you know to be equivalent to it in whatever you're working with. And in these exercises, we want to take one and show that it's equal to the other by simply replacing it with these known identities or using rules of algebra. Okay, that is it for this one. Thanks, everybody. I will see you next time.